Know what the most frustrating part of my design project is? Synthesis. I've got tons of pressure from management to get the design done. And all these complicated timing constraints, functional considerations, and layout dependencies. And I really want to work hard to get this project finished on time. So, I get my design and constraints ready, push the button, and wait. I take a nap, watch a few YouTube videos. My boss comes in and thinks I'm slacking off. Then finally, I get the results back and have to do a bunch more stuff quickly so I can hurry up and wait again. Synthesize, wait, rinse, repeat. Forever, it seems. Hi, I'm Amelia Dalton, host of Chalk Talk. Today, synthesis is one of the most important and challenging parts of our design, and we end up spending a lot of time iterating and waiting for those iterations to complete. But help is on the way. My guest today is David Stratman from Cadence Design Systems, and we're going to talk about how Cadence's new Genus Synthesis Solution can dramatically improve my life and yours. Before we get started, don't forget to click that link. There you can find out more information about Cadence's Genus Synthesis Solution. Hi, Dave. Thank you so much for joining me today.
It's good to be here. Appreciate it.
So just about every Chalk Talk we do, we talk about how big and complicated designs are getting. And I noticed that Cadence uses the term productivity gap. Now, what exactly does this mean?
Well, it's kind of a function of two things, really. If you look at the trends in design, certainly the complexity of the chips are going up. The end market requirements, as you have this intersection of kind of mobile, cloud, Internet of Things, and they're squeezing so much more into a chip, but the design teams are really kind of a fixed headcount.
Right.
Or they can grow, but it's quite expensive to grow your design team exponentially as your block grows.
Absolutely.
So there's always this challenge of how I partition my design and how many engineering resources can be used, how productive they can be to crank out as many blocks or partitions that build up SoCs as they can in a given design cycle. So it's that gap in productivity that we feel the current generation tools struggle with. Oftentimes for the larger blocks, some of these design teams have to wait up to a week to get a result through the full digital flow, and that's painful, it's costly, and it's something that we're trying to help solve.
Okay, let's talk about synthesis in particular. Now, what does this mean to the synthesis part of our design process?
There's actually more than one synthesis if you think about it. There's a lot of different users running a synthesis tool. If you look at a large SoC, there's a number of blocks that we've partitioned up into. Typically today, those are in 1 million to 2 million placeable instance sizes for your more complex SoCs. And there's generally a large block level synthesis that's done typically by a back-end engineer, an implementation engineer, or someone whose specific job is to integrate units from RTL designers. Then there's all these other RTL design synthesis happening across oftentimes different parts of the organizations, different parts of the world, where you have individual logic designers working on their modules or unit levels. These could be much smaller blocks that together build up a individual SoC partition, but run much faster, and they can maybe run 10 to 20 synthesis runs a day, and they're developing their RTL. Generally, they've been more focused on the logical, functional results of that RTL block as opposed to how you close timing, how it fits into the physical block itself. And then there's this kind of iteration down to place and route from block level where we have to do a lot of additional synthesis runs at the block level if timing doesn't close through place and route or you have congestion issues, et cetera. So in general, we see there's a whole lot of opportunities to get stuck in the digital design flow, and each one of them has some unique characteristics because it's different types of synthesis runs.
So I assume that since these slides say Cadence at the bottom, you guys have something in this space?
Yeah, we do. We've actually just recently introduced a brand new synthesis tool that we built from the ground up to be massively parallel, scale extremely well to help tackle that productivity gap. The product is called Genus Synthesis Solution, and there's 4 areas that we really tried to focus in on in this initial release. The first is across the board the turnaround time through a complex synthesis run.
Okay.
And so we've added some new technology that looks at multiple ways to parallelize and looks at the problem of partitioning and how you handle partitioning and reintegration more efficiently in order to deliver that turnaround time without degrading QOR. And then secondly, there's this loop between the unit level RTL designer and the block level synthesis engineer. And in that sense, we looked at ways we could enable some of the timing and physical visibility to provide a scope for those smaller unit level block synthesis runs in order to ease the communication and transition between those two stages in the flow. Another big part of productivity is how accurate are the results you're getting early in the flow. So, for example, timing, wireline congestion, all these things, we need to ensure that they're consistent and hold up as we move through place and route. So there's things we've done in sharing algorithms, et cetera, to address that. And then additionally, we're always looking for opportunities to push PPA because it's this constant trade-off between, while we're trying to improve productivity and get more done from a design team, at the same time, the end goal is always to get a chip as small and as fast as possible.
Sure. Okay, synthesis has always been one of those problems that's hard to parallelize. When we try, the quality of results always seems to suffer.
Yeah, it's been a hard problem algorithmically for some time. There's probably been 20 years of research on partitioning and parallelization. The challenge, though, is how you can maintain QOR or PPA as you take that end result integrated back together.
Right.
So we've come up with a couple really innovative solutions here. It's kind of some secret sauce we feel that's patented in how we cut the design, how we do the partitioning intelligently.
Okay.
It's really this long pull effect in the design where you could partition based on area, equally sized blocks, but one of them may be much more timing critical than the other. And therefore the effort of synthesis that goes into that block may be 5 times all the others.
Sure.
So the others finish real quick and you're waiting for that fifth, and so your overall turnaround time doesn't improve. So it's this leveling and balancing exercise to determine how to intelligently partition. That's really a hard problem to solve. And then integrating those partitions back together without losing any of the information of the full chip scope to not degrade QOR. So we took an approach that actually broke up the problem, and we do a high-level partition of kind of larger blocks, and we take that block all the way through the synthesis flow. And then inside those partitions at each stage of the flow, like mapping and structuring or incremental optimization, we can sub-partition those into smaller chunks. Each of those 2 partition stages can be threaded to different threads on a CPU, but it can also be distributed to other CPUs on a server or even other servers on your farm or on your machine. So it really allows us to scale quite well to a high number of CPUs as you increase design size. And then finally, we have this low-level, algorithmic level shared memory multi-threading that's also been developed on all of our engines. So really these 3 levels work in concert to improve the turnaround time of the synthesis flow, both logical and physical. We've had to add a brand new scheduler to think about how to deploy CPUs most efficiently. Do you use technique A or B or C, depending on the type of design, partitionability, et cetera. So there's a lot of research that's gone into that adaptive scheduler as well, and we're encouraged by the results.
Cool. So I assume that if you've got parallelization going, the results must reflect this, right? Are there specific types of designs that this would be good for?
What we found on a wide range of customer benchmarks that we've engaged with to date across different design sizes, different speeds, varying process nodes, and really different application markets, we've seen very strong speed up across the board, between 3 and 5x over those designs' previous production synthesis flows.
Okay.
So whether they be ours or competitors, the turnaround time improvements of Genus in any reasonable size block are holding up quite well for that block level synthesis. This is again allowing the customer to reconsider what sort of partition sizes they may be able to use in their designs and really kind of create some new strategies where they can more aggressively move to 5 million, 10 million instance blocks and still get results in reasonable time frame that are production level from a PPA perspective. So again, early results are highly encouraging across multiple design styles.
Okay. So these numbers look really good on a block level synthesis, but what about the RTL guys running their modules 20 times a day?
Good question. Sometimes that synthesis run is not as complex. If you consider a typical block in an SoC, an example here looks at that block being comprised of 3 different units, colored in red, blue, and green here. Typically, those unit level synthesis runs are just done logically, and then they're kind of thrown over the wall at some regular frequency. Maybe you do all the unit levels work on their designs over the week, and then they give it to their top level integration expert, whether that be a backend guy or an integration guy, and they do that top level synthesis or block level synthesis, and then understand, okay, designer one made these changes, they impact timing over here, he has to go clean up his RTL, I'm going to write him an email or set up a meeting, and we'll go through all the timing reports. It's typically this kind of onerous, painful process where the logic guys don't necessarily want to play in the physical world and deal with timing, so they really push that problem off. And then other customers we've engaged with, that cycle is even faster, where they'll do runs during the day and they'll do an integration every evening. So either way, there's a lot of loops back and forth. So what we've identified, and I spent a good 10 years as an RTL design engineer and tried to avoid that same problem that a lot of our customers do. That's the backend guy's problem. But realistically, at advanced nodes, you can no longer take that tact. You have to start considering some of these effects at unit level synthesis, or you'll really be stuck in these iteration loops over and over again. We developed something that we're calling context generation. And so for each of these unit levels in the block here, we can generate the floor plan scope around that block and all of the input-output timing, essentially cut the timing graph beyond just what you could find in SDC, but full timing graph with false paths, etc. And then provide that essentially as a wrapper. We generate it from one command as part of the block level synthesis for any units that we want to create this clip, we're calling it, kind of clip out the context. And then the unit level engineers can run their unit level synthesis with this, essentially replacing their logical synthesis scripts, so that all of the timing analysis they're doing is in the context of the real physical design and the blocks around it, but we still have the productivity benefit of working down at the module level.
Gotcha.
So typically we've seen almost a 2x improvement in the number of iterations between block and unit level. Wow. Some of our early partners who have large RTL design teams are really encouraged by deploying this flow. And it's making the communication between the front-end RTL user and the block level synthesis engineer significantly more streamlined.
Okay, Dave, so I've always had this problem that everything looks good through RTL synthesis, and then when I go through place and route, everything goes out the window.
Yeah, I would say you're not alone in that. It can be definitely a challenge in avoiding timing jumps and congestion issues downstream, especially when you're running a purely logical synthesis from an RTL perspective. We're encouraging our customers for some time now to move to a physical synthesis flow. And Genus has a new physical synthesis flow. We actually introduced a number of new products recently at Cadence, and we have a new place and route engine called Innovus as well. And this was an opportunity to really levelize and determine, can we do a better job of sharing the engines and algorithms in order to avoid those type of timing, congestion issues that customers had seen in some instances, even when running our prior generation physical synthesis flows. And so we looked at kind of everything across the board and did an audit. And now in the next generation, we're sharing a number of key engines. So a placement engine, GigaPlace from Innovus is shared in the Genus synthesis stage. We're actually using the same algorithms, but we're operating at generic gate level. So we do a very early placement before we've actually even mapped into library cells, but we use that scope for all of the steps of synthesis so that they can be a true physical synthesis run. Similarly, we've now shared parasitic extraction, delay calculation, and we now actually do a detailed model of the routing even at the synthesis stage. At advanced nodes, that's becoming a requirement, so we understand which metal layer the route is intended for, as the resistance capacities can vary greatly from one level of metal to another, and therefore the timing can be quite different. So overall, we're using this approach to improve the correlation, and we're seeing results in 5% for all the key metrics. Other thing I wanted to note, though, is that really the first level order of correlation is the user interface itself. And if a tool is inconsistent from front to back on how it reports a metric, for example, it's hard to debug where the issue is. So starting with Genus and Innovus, we now have a complete common user interface. So all the initialization setup is shared between the tools, common database access, common reporting, etc.
Cool.
This goes a long way to improving productivity and training from engineering teams. So if you had a synthesis expert, they could start dabbling in place and route because the tools and commands feel very similar. And this extends down to our Tempus timing sign-off solution as well.
Excellent. So sharing these are great, Dave, but what kind of results can I expect? Even using a physical synthesis flow, there are still outliers when I move into place and route.
It's true, and it's really kind of never-ending problem. At each new node, you need to reconsider
Right.
which physical effects you're going to model to deal with those outliers. We kind of live in this scatter plot world where from front end to back end, we're always looking at probably 10 plus key metrics, how we degrade from synthesis results to the end of place and route. And we try to, ideally, if we modeled all the physical effects with the full runtime implications of a P&R tool up at the synthesis level, we could correlate exactly if we wanted to. But then you'd be running about 5 times slower than you would expect at the synthesis front-end
Right.
stage. So we have to choose at what level to model. And each new node, we have to reconsider that. Again, with Genus and Innovus, we had an opportunity to kind of realign a lot of the key engines and share code as much as possible. What we found in our previous generation physical synthesis and place and route tools was that we correlated fairly well. It was actually one of our strengths for the top line metrics, things like frequency, total wire length. But when you started to dig a little bit under the surface of the real things that design team needs to get correlated to close a design, things like TNS or 3 sigma path delay or pin-to-pin wire length instead of total, while we were still reasonable, we started to see certain designs where we had outliers. And so that's where we realized we have to be more intelligent about sharing routing, exact placement, etc. And so now with our next generation flows on Genus into Innovus, we're seeing the correlation much tighter between 2 and 5x better than our prior generation, which was already very competitive in the industry. So we're encouraged by these results, and we're going to continue investing in this area. As like I said, it's a moving target.
All right, so we've talked a bunch about productivity, but really, Dave, I'm normally measured on how big my die is and how expensive it is. What can Genus do for me here?
Fair enough. And that's a problem that we're trying to focus in on as well, because it's absolutely true. As fast as we can make a tool, if the results degrade, we're really just kind of a prototyping synthesis tool. We don't want to be that. We want to be the fastest production synthesis tool out there and give the best possible PPA result. So there's a couple of projects that we've been working on. And the first one that's being deployed in the initial launch of Genus is focused around area and power, specifically on the data path.
Okay.
Design like GPUs or networking chips where you have a lot of heavy data path. We've developed some pretty novel new solutions to optimize those data paths for area. If you're familiar with Cadence's synthesis solution, for some time we've had a really innovative approach to the way we've done our logical mapping into library cells. If you look at like kind of pure Boolean graph, we have what we call a global mapper where we characterize all the potential cells we could map to ahead of time, and then we globally analytically solve up for the best solution to choose all of those cells. We realize that because we have that baked into our database and kind of the DNA in our synthesis software, we're able to extend it up to the word level or the functional level. So instead of being down to the Boolean level, we're up at the word level looking at multipliers, adders, muxes. And so essentially we're identifying these data path regions in your SoC.
Yeah.
And partitioning them through some of these new partition techniques we talked about earlier intelligently beyond just module, logical, or physical hierarchies to identify the key regions. And then we characterize all the potential implementations. You could have a very fast adder or a more efficient from an area or power perspective adder. And there's many along that curve in those multiple constraints. And so we look at all the potential essential microarchitecture implementations of all of these stages in a data path region. And then we can globally solve, again, is it better to have a fast multiplier in the beginning or a fast add at the end? And what's the trade-offs between those so that you can get the lowest possible area solution that still meets your timing goals? Again, this is kind of leveraging some of the underlying benefits we've had in our global mapper for some time to do RTL optimization in a similar technique.
Okay, so I think I get the concept, but what kind of results is this really going to get me?
We're still gathering data here, but the customers we've engaged with so far, and specifically we're targeting essentially a benchmark suite that is, I would say, data path heavy class of designs. We're seeing on average nearly 20% area savings in that category designs, which is pretty significant when you're talking about that cost challenge.
For sure.
If you have a number of blocks that are maybe reproduced, replicated heavily throughout your design, and you can get 20% savings, that's going to directly affect your die size, your bottom line. You generally you're able to be more aggressive in kind of shrinking that die.
Yeah.
So we also have some case studies on specific customer designs. For example, this video codec, we're able to see pretty strong area improvement, but also still deliver that runtime, turnaround time improvement that is one of the key tenets of Genus, and not impact timing. It's that trade-off of how fast can we get the tool, how many instances, how many CPUs can we get to scale to, but still deliver production level PPA.
Gotcha. So, Dave, do you mind giving me a quick recap?
Yeah, no problem. There's 4 key areas that we think Genus really shines on. First is massive parallelization. We're able to scale well beyond 10 million instances. We recently synthesized a 35 million instance design in a matter of days, something that was just not even feasible or something we could consider in previous generation tools. But again, delivering this with production level PPA is the key and really the hard problem to solve. And then we're focused in on the RTL designer with Genus. We've added some nice new functionality to deliver fewer iterations between that unit level synthesis RTL designer and the block level integration engineer. What we've done is we generate these physical contexts for the unit level engineer to be able to take advantage of the physical scope without becoming a physical synthesis expert. Thirdly, we really doubled down on correlation, and we used the introduction of both Genus and Innovus as an opportunity to align engines across the board from front to back within Cadence. So routing, extraction, placement, all of these things are now shared to some degree. It's delivering really strong results in correlation, generally in 1 to 2% of all the key metrics you would expect: timing, wire length, congestion. And then lastly, all that productivity is great, but end results are also what we're measured on. And so one major feature of Genus is this architectural level PPA solution where we focus in on key data path regions, squeeze as much area out of them as possible, but still meet your timing goals. We've seen on average nearly a 20% reduction in area, and certainly anytime you're reducing area, there's also a power benefit as well.
Great. Well, I think that's all I have time for today. Thank you so much for joining me today, Dave.
I really appreciate talking with you. Thanks.
Before we go, don't forget to click that link. There you can find out even more information about Cadence Design Systems' Genus Synthesis Solution. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, check out EE Journal's YouTube channel, keyword EE Journal, or the on-demand section of eejournal.com.